So, long time no live stream. The topic today is RaptorJIT Intermediate Representation code and how we look at this in Studio. So Studio is the visual diagnostics suite that I'm working on that's written in Pharo Smalltalk. I'm starting to say Pharo now instead of Pharaoh. It seems to be what everybody else says. It's a visual graphical tool for understanding internal data structures of the RaptorJIT just-in-time compiler. And RaptorJIT is a fork of LuaJIT that we're working on in the Snap community. There's quite a bit of support for RaptorJIT inspection in Studio now. It can take a lot of JIT internal data structures and present them in different ways and do some cross-referencing and visualization and that kind of thing. It doesn't do everything yet that you get out of the textual dumps from LuaJIT. So on the one hand, it's kind of catching up on some of the basic features that you had in the text dumps. It's covered most things, but not everything yet. And on the other hand, it's kind of doing some new things that are possible in the graphical environment that wouldn't be practical otherwise. So it's kind of a racing on two fronts there. And the topic I have in mind today is snapshots. So first I'm going to do a little bit of a demo of the GUI, and then I'm going to look at how we should incorporate snapshot information in. So a snapshot is starting with the first thing we're going to look at is the intermediate representation of the code, and I'm going to dive into this really shortly. How does compiled code look to the JIT compiler when it's doing its optimizations and so on? What's the representation of the program that it's working on? This is a really important thing to understand. If you want to be an expert at optimizing code for the JIT, you want to be able to see the code the same way that the compiler sees the code, so you can see anything that doesn't compile the way that you would like it. You can see why that is and how to correct it. That's a big part of Studio is as a kind of a power user profiling tool to be able to really get on the same page with the compiler and how it's executing your programs. And snapshots then are a kind of a supplementary bit of information. So the compiler takes code and it compiles it into a trace of machine code, which is very kind of inlined and tightly optimized. But at any given time, this tightly optimized code might need to bail out to some other code. So the machine code that the JIT generates is very, very, very specialized for a particular path of control, particular types of arguments, and all of that kind of thing. And if you have a lot of variation there, a lot of unpredicted, unbiased branches, and different types for the same variables and so on, you get a few different bits of machine code, and some of them some parlors might not even be able to JIT compile. If you reach an error case, for example, then the JIT probably bails out to the interpreter and lets it do the exception handling. And in those cases where the machine code needs to bail out back to the interpreter, what you need to do is reconstruct the stack the way it's supposed to be. So Lua keeps everything on the stack, basically. The virtual machine has a stack where it puts basically everything, and all your local variables go there. So when you call a function, you allocate a little bit of space on the stack for all of the local variables that you need, and you put all the values there. So in principle, the state of execution of a program is, a larger component of it is on this Lua stack. But in the machine code, the stack's not being maintained because you're keeping things in machine registers instead, and using the native CPU stack, which is basically the C stack. So while machine code is executing, you're not actually maintaining this data structure for the interpreter. So what that means is that when machine code needs to transfer back to the virtual machine, the bytecode interpreter, then it needs to reconstruct the stack as it is supposed to be. So every value that's stored in a register or on the CPU or C stack needs to be poked back into the right place in the Lua stack, so that if you get an exception, you can generate a stack trace and you can debug. You can look at the values and local variables and all of that kind of thing. So snapshots exist to support that operation. A snapshot is a description of how the values that you have in local temporary variables relate to in registers relate to the logical Lua stack. The snapshot tells you how to reconstruct the Lua stack from what you have in registers at any given time. So if you're calling some functions, you're calling some subroutines, then when you reconstruct the stack, you'll need to include those kind of stack frames. And also if you have some local variable values or any values at all stored in registers that haven't been committed back to the stack or the heap, then you also need to flush those out and take them from the right register and put them into the right stack slot and that kind of thing. So the snapshot tells you how to do that. I think I'm talking too much. I think it might be easier to do this stuff while kind of dived into the code. So maybe we'll do that. Maybe we'll do that right now. We'll pull up my little to-do list, as I like to do. And we're going to first do a demo of the Studio UI, just so that we all know what we're talking about. And I can review some of the features that have been added recently. Then we're going to look at what snapshots really are all about. What is the data structure? How does the JIT represent the snapshot? What details are there? And then, if we can think of the right way, maybe starting simple, we'll hack something into the UI to display snapshots, but for a user perspective. It'd be kind of neat. So, away we go. I have to resize my studio window because the live streaming desktop is tiny compared with what I usually use for programming, but it has worked out okay in the past anyway, even with very modest screen real estate. Let's hope it works well for us again today. Oops, I've got a lot of debuggers and stuff open now, so I can just close a lot of those unneeded windows. But I want to keep this one. Maybe we'll just start. Remember the number 2562. 2562. That's the directory we're going to browse for data. I'm just going to close those windows because I've been doing a lot of hacking in this Pharo image. This is the Smalltalk image. This is the thing. This is the kind of the behind the scenes view. Normally, when you're working with Studio, what you'll see is the Studio Inspector. And it will normally be full screen. So there we have one. Let's shrink it a tiny bit there. Okay. So this is the inspector where we enter a NIX expression of all things. To produce some data that we want to process. So NIX is a kind of like a make on steroids kind of thing. So you can enter any NIX expression here. And in our case, we're going to say snab.process directory. And what was that number? It was 2562. I don't remember. I'm going to have to check. 2562. Yes, it was 2562. So here we can actually enter any NIX expression. So in principle, we could go off here and build a whole virtual machine image and run it in QEMU where it could be running, we can do anything here, like your imagination is the only limit. But we're going to do something simple, which is to call our predefined snab module, which is a bit of code, and we're going to look at inspect the directory from a snab process. Yeah, so this is this is actually a snab process that ran on the continuous integration server, and when it terminated, it just left its internal state in a directory, and I downloaded that and unpacked it in my home directory. And now I'm going to click open that, and it goes off, and it does some pre-processing, and now it's loading the audit log, as it's called, from the RaptorJIT virtual machine. And here we have this kind of Miller columns thing here. So on the left, we have the first thing we were looking at, and then we ran something that popped up to the right, and this is something that just continues. So if we select something here, it's going to pop up to the right, and we're going to get this series of columns where we can drill into things. And we've got a few tabs here. Well, what are we going to say? Sorry, let's back up a bit. We ran this next expression. It inspected a directory that contains a snapshot of the internal state of a snab process. So snab is a RaptorJIT-based network stack, a RaptorJIT-based application, and snab, when the application runs, it creates a directory and it stores a bunch of internal state there. And if you save that directory, then you can load it into this graphical studio tool and have a poke around. And that's what we've done here. And what we're inspecting here is a RaptorJIT process. And we've got a few different ways that we can look at it. We can look at its profiler data. We can look at its events, individual events, but that's a bit too detailed. So if we just start off by picking something potentially interesting in the profiles, we can see how for each kind of subsystem in the program, we can see how many samples the profiler took. It's a sampling profiler. It takes a sample every millisecond. It's saying it noticed about 839 milliseconds of activity spent in the engine, and then in these other kind of subsystems. And then for each subsystem, it's also telling us how much time was in machine code, how much time was in other virtual machine runtime system work, which might be running the interpreter, it might be other things, anything that the runtime system handles rather than inline machine code, and also finds garbage collector activity. So just for the sake of poking around and getting to some intermediate code, let's pick the engine, hop in there. Oops, I really need to have Slack open, do I? But Slack, where we all hang out, do semi-live coding. Back here. So now I picked the profile I'm interested in, the engine, and now I see the root traces. These are lines of code in the source code where the compiler woke up and started generating a tree of fragments of machine code, and I can pick one of those, and I can see the individual fragments here called traces, which are each identified by number, and I can browse them. So as I was saying, we've got on the left we have the first thing that we started looking at, and then on the right we have the next level in. And if I select something here, like trace number 20, which is the root of all these machine code fragments, traces, then that pops up over here. So if I expand this out, you can see that really we have 3 panels now. We have the first one there, where we entered the expression saying what we want to inspect, and then we have this one here where we selected something from the profiler, and then when I drill into something here, then that popped up over here. And now this is a list of bytecodes, individual bytecodes that were executed in this fragment. So what we're seeing here is we've got a fragment of machine code. It starts, well, I'm going to shrink this down a bit. So we've got 3 panels, but I only really have screen real estate to show 1 or 2. So I use this little slider to say how many I want to see at once. So there I got 3, there I'd have 2, there I'd have 1. So I think 2 is a nice compromise. So this is a bit of machine code that is a loop in the source code that starts on this source file line, and for this chunk of machine code, it corresponds to 1 path of control through that loop. And the recorded bytecodes show you line by line every step of control that this takes, and you can see that it's not always in the same module. So it comes down in this app.lua source file, and it goes into vhost user.lua, and then it comes back in. So you see the stack depth here. So everything is getting inlined is the message here. So when the compiler wakes up and starts recording things, it inlines everything, and then when it gets back to the top of the loop, it says, well, okay, now I've inlined 1 path of control through this loop. Now I'm going to generate code for that, and the code is this intermediate representation, and that's what we have here. So this is the most important representation of code in the JIT compiler, and I want to have like a 2-minute spiel about how the whole IR code thing works and a nice introduction, but you'll have to consider this a warm-up of that. So you have 4 levels of 4 different representations of code in the JIT compiler. You have source code, which is then compiled down to bytecode in a very kind of predictable, static way. You take source code, you compile that to bytecode. Then the bytecode is interpreted, and the next step is to get to the intermediate representation, which is what we have here. And this is not static. This is a dynamic process. So you actually execute the bytecodes, and as a side effect, you generate the intermediate representation code that then says what those bytecodes did in that particular run. And then from the intermediate code, you generate the machine code. And by far the most important representation is the intermediate code. The reason for that, the basic reason for that is that the source code and the bytecodes, it doesn't have any dynamic information. There are infinitely many different ways that source code and bytecode could be compiled depending on how it actually runs. What the types of your arguments are. If your arguments are strings, if they're integers, if they're foreign function interface pointers, And when you pass around higher order functions, the code you get is going to depend on what function you're calling into. So there's a lot of details that are only known at runtime, and none of that is represented in the source code or the bytecode. The source code and the bytecode are essentially debugging aids. They don't have that much to do with how the code executes, but as a programmer, when you want to understand the lower domains like the intermediate representation code, you want to map that back to the bytecode and the source code. So the intermediate representation code then, it contains, in the IR code, you can see all of the optimizations that were done. You can see all of the type information that the compiler inferred and decided to rely on for that specialized piece of machine code. You can see a lot, and then on the machine code level. So in some sense, machine code is the most fundamental. So you might think that if you really care about details, you would look at the machine code, but it's not really true, because the mapping between the intermediate representation and the machine code is actually quite predictable. So it's important to have a feel for how each IR instruction translates into machine code. But once you have that feeling, you don't need to look at it again all of the time, because all of the really fancy, funky, clever optimization stuff is represented in the IR code. And once that's been done, the translation to machine code, the assembly, is a much simpler and more straightforward proposition. So basically, just by looking at the IR code, you can understand in a really deep level what the compiler is doing with the source code. So IR code is the most important thing when you are doing advanced program optimization. So we need to have tooling support to understand the IR code. So now let's look at why it's not trivial. Hold on. The IR code is not trivial because look at it. It's a detail. So I'm going to scroll down here a bit, and it's kind of like a high-level bit of assembly code. So this is in static single assignment form. So for each instruction, this is a list of sequential instructions in the order that the logical program order. We have an opcode saying what operation is being performed, and then we have up to 2 operands. And the operands, in this case, they're constants with the hash sign. And on other instructions, you get a reference to an earlier instruction. So instructions that produce a value, like sload, is loading something from a slot, like a local variable, for example. This has a value, and this is referred to in the IR code by the number. You say so here, when this is performing a guard, it's doing a less than or equal check, comparing this constant with the result of instruction 0001, which is this instruction here, which we can see is the value in the RBX machine register. So in the IR code, when one instruction wants to reference the result of an earlier instruction, it does this using the instruction number, and the compiler behind the scenes will then look at the register assignments and understand that that's in RBX. Now this is a pretty low-level view, and how many instructions do we have here if we scroll down? We've got 118 instructions, so it's quite a few, right? So to sit down and read through 118 instructions, it's something. So what I want to do in the studio tooling here is to make this a little bit easier. And there's a few different ways to do that. One way is to kind of try and get an overview of what's going on, so that you can kind of look around and see what's important. Another way is if you already know what you're interested in, if you're looking for allocations, or you're looking for calls to external C functions, or anything really specific, another way is to make it possible to zoom in on those things. So I've tried to create a few. Well, another thing is, if you see an instruction that's interesting, after you've found it, it's nice to be able to prune away the irrelevant details and get a closer view of what's happening there. So I'll just do a little tour of some of the ways that we have to do things. The first thing that I added is so this is the intermediate representation IR list. We also have a tree representation of the same information. If we pick the tree, got to zoom out a bit, then this is a diagram, and I'm on a small screen, and I've had to zoom out quite a bit, but this is just a diagram representation of the same thing. So if I select a region here to zoom in on, then, well, that might have even been a little bit too big. this little screen, even smaller region, then I can see visually some of these instructions. I can see that those are not especially self-explanatory. Let's pick this little tighter cluster up here. So here we can see a little bit of how the code connects together. So, for example, here is a call to an external function, FFI function, and one of the parameters is a constant that we see there. The other one is a field that has been loaded from a hash table load, which had a key, which was the literal string engine, a constant key. And this came out of a field loaded from something that was loaded from a closure, and the closure was from the function defined at apt.lua85. So we at least see here a little bit more of a connection, right? We see an external function call. We can see the chain of we can kind of see where some of the values are coming from, but it's still pretty tricky, right? And the thing here is just to see the structure of the IR code. It is a tricky thing. So supposing we wanted to zoom in a little bit more, we say this is the instruction that we're interested in. We're really interested in this call. Then we could select that now, and we could see its inputs, the input tree. So this is just a way to kind of try and prune away some details to make things a bit more understandable. So when we look at the inputs tree, it's taking this instruction and it's computing the transitive closure of all of the inputs, which is to say any instruction that this one refers to is that fload, and then recursively every instruction that's referred to back. So now what we see in this picture is all the chain of things to see where the input to this comes from, and nothing else. So we take away everything else. So this is something I'm finding a little bit handy. If I see an instruction of interest, it might be. What if we have any allocations here, for example, as well? That's another external call. Just find another instruction as well. Here's another call. That's to the same function. Oh, okay, well, we'll stick with this one. Anyway. So, okay, that's one way to look at things. You can prune the tree by just looking at inputs. And I find this helpful because we can also look at this as a listing, input list here. And there we see the IR view as text, which is maybe quite nice if you're used to reading disassembly and stuff. But the good thing here is we see only the relevant instructions. So it's instructions 72, 70, 67, da-da-dum. So it's a nice little sparse list here. So, I mean, it's a span of quite a few instructions, and if we go back over here and look at it kind of all the way zoomed out and come to instruction 72 here, then we need to mentally filter everything out, right? Because these are interleaved with a bunch of other things. So if all that we want to know is where do the inputs to this external function come from, then it's a little bit nicer to look at that here rather than here, when actually there are 70 instructions that could potentially be there. Anyway, the other kind of handy way to look at things, I'm going to go back to the tree representation because I like it, is we might see a value along here somewhere. We might say this value that we load out of the hash table, out of the engine hash table, I'm interested in that. I want to know more about that value. So now I can click on that value, and now I'm seeing its input tree, and of course this is a subset. This new zoomed in one is a subset starting from the H load going up. So it's just the same here going up. So if I zoom in on this one, it should look the same, basically. Anyway, but then having picked this as the main instruction, we can also look at the uses. And so the uses then is the opposite of the inputs. So if I want to see the uses tree, then instead of going upwards to see every instruction that this H load takes input from, it goes downwards. So it's the transitive closure of every instruction that refers to the result of this H load. So now I see what else are we doing with this value. So I see that we have this call. We do this hash table load. We load a pointer field out of that, and we call this as a foreign function interface function. We also check that it's non-null. So you can see the JIT compiler there is doing a null check on that value, comparing it with a null pointer. Can also see that it is checking for the pointer there. The pointer that gets called is also called down here in the loop, so it gets called outside the loop and inside the loop, which I guess is natural for a foreign function interface call, because it's well, the JIT has got a it's got a kind of a from scratch. I'm digressing, or am I? I don't know. This is important. The JIT has compiled this into a looping trace, so that it's the block of machine code is something that loops, and it's got one set of code for the first iteration of the loop when you're kind of coming from a clean slate and you need to do everything from scratch, and then it's got a second compiled representation for the second, third, fourth, and so on iterations. And the basic thing is that in the second iteration, you can reuse a lot of values that you already have in registers from the first iteration, and you're doing anything that doesn't kind of need to be done on every iteration. It only needs to be done once, and you already did it in the first loop, and then you can skip that. So anyway, we see that this field, this pointer that we loaded out of this field, and there's a tooltip there as well telling us that fload is an object field load, and that the result here is a pointer and giving us the instruction number if we want to go back and cross-reference this in the IR listing and that kind of thing. Anyway, so this pointer, C function pointer, gets loaded there, it gets called in the first iteration, and that call is also present in the later iterations. And we had a guard here to make sure it was not a null pointer. And I guess if we go into the users list, we can do the same thing for all of these things. You can flip back and forth freely and mix and match between the visual and the textual listing and any other listings we invent, or visualizations we invent in the future. You can see that actually in program order we check that it's not a null pointer before we make the call. So that's presumably if we had a null pointer there, then it's gonna use the snapshot to reconstruct the stack and for the Lua virtual machine, and it's going to transfer control back there and execute some kind of error handling, exception handling, rather than seg faulting, which is very nice. So maybe that's a reasonable segue into snapshots, because this is kind of a view of how the IR listings work now. So the next step that I want to put in here, the missing information, is the snapshot. So when we're looking through these IR listings, how do the values that we have in registers relate to the logical values that we need to have on the Lua stack? And how do we reconstruct the Lua stack? And what can we do with that information? It's also kind of, in some sense, the snapshots are an internal detail, and in principle, we could ignore them. We might say, who cares about snapshots? That's just some internal detail of the VM. But the reason to decode them is that there can be actually interesting, useful, actionable information there. And the main information that we would look for is if an allocation, for example, is not optimized away. If we create an object, we create a table or something like that, and we actually heap allocate that and call the garbage collector, we might want to understand why that allocation wasn't optimized away, and that might involve seeing how it's used and whether it needs to be stored on the stack to be passed somewhere else. And we also might be able to get a bit more insight into which parts of the program are running. If we see how the control stack would be reconstructed at any given point, then it tells us where in the program we are, which subroutines are on the stack. So if we call subroutine 1, subroutine 2, subroutine 3, then the snapshot at any given point is going to say how to reconstruct that. So it's going to tell us where we are in the program. So I'm going to take a break for 5 minutes and then come back and dive into starting off looking at the really internal representation of snapshots in the virtual machine. And then we'll see if we have some snapshots in this GUI that we can start poking at, and we'll see if we can find just a simple way to represent them. Back in a minute.